morning. In my last lecture, I was talking about catalyst deactivation. So, I will continue the same today also. I discussed the catalyst deactivation, that the decrease in the activity of a catalyst with time on stream, and this may happen because of the poisoning, fouling, and sintering. So, poisoning is because of the presence of the poison precursor, right. That may be in the feed itself, it may be a product during the reaction, and this is a kind of chemisorption on the active site of the catalyst, and thereby decrease or destroy the active sites of the catalyst permanently. In the case of fouling, it is the deposition of dirt or mainly the coke material. So, also known as coking. So, carbonaceous material on the surface of the catalyst during the chemical reaction. So, because of this, the activity of the catalyst decrease. However, this coking is a reversible process, or the coke burned on the coke can be burned by using the carbon plus oxygen reaction, and you can remove the carbon from the catalyst. So, regeneration is possible in this case, right. The third case is the sintering, which is because of the high temperature and time. So, crystal size grow and the pores may destroy because of the long term duration when the catalyst is used in the reactor at high temperature. So, basically it is a recrystallization of the active centers of the catalyst. So, generally when you have, so you need to give some treatment in order to regenerate the crystal structure of the catalyst. So, sometimes it is possible, but sometimes very difficult to regenerate the catalyst in this case. So, depending upon the kind of the poison precursor or depending upon the type of deactivation in a catalyst, the mechanism may be different, and that is known as the deactivation mechanism and related to some function which is known as deactivation function. So, mechanism of coke formation, when I say the carbon formation, it can be depending upon, it can depend on the type of the feedstock, it depends on the temperature or reaction conditions, and the mechanism may be different, and accordingly the amount of coke formation on the catalyst may be different, which I discussed last time also, that it is a kind of asymptotic coke formation during a hydrocarbon conversion process. So, this is the amount of coke formed on catalyst as a function of time on stream, and can be written some C c is equal to A times T to the power n by some empirical correlation, right. So, n can be 0.5 and this can be 0.46 or 7.5. So, they are different depending upon the type of the feedstock and temperature conditions, this may change. So, in general what I said, that the coke formation mechanism exactly need to be established or discussed for a given hydrocarbon for a given reaction over a given catalyst. So, in that case there are some common expressions which are generally used to correlate the rate, because I told you that rate at any time t for the main reaction is rate at t is equal to 0. So, multiplied by the activity or the deactivation function of the catalyst. So, this is the deactivation function and this is the rate when the catalyst is fresh. So, this is what here, if you look at, this is the rate when the catalyst is fresh, and this is a kind of activity A, which is defined generally in terms of minus dA by dt is equal to kd to the times A to the power n times some feed concentration or the coke precursor concentration. So, the different mechanism may be available to define this value of phi, and this is a kind of Langmuir-Hinshelwood-Hausen-Watson expression which we have discussed earlier, that this is a kind of temperature dependent term K 0, which is the rate constant for the reaction. These are the thermodynamic equilibrium constants K A and K B. C A is the concentration of the feedstock and C B is the concentration of the product, and this term is known as driving force for the reaction, which we have already discussed. So, when you need the kinetics for the deactivation reaction, or when you want to find out the activity with time on stream, so one needs to write a mole balance equation as usual in the reactor design. So, this is a kind of mole balance equation here, F A naught dxa by dz is equal to minus R A times A C, or one can write it F A naught dxa by dV, because AC into dz is dV, volume of the reactor in differential form, and that is minus R A, rate of reaction per unit volume of reactor. So, one can write this expression in the form of per unit mass of the catalyst also. So, that time it becomes F A naught dxa by dW is equal to minus R A dash, where R A dash is rate of reaction per unit mass of the catalyst. So, this is true for a stoichiometry, which is given here. A converts to B, which is a product, and C is a solid material, a carbon, right, or coke. Concentration expressions, all of you know now, Ca is equal to Ca naught 1 minus Xa, because it is a constant volume system here. 1 mole of this gives you 1 mole of the product, which is generally in the gaseous phase, and Cb is the moles of B formed. So, that is reported in terms of the conversion. So, Ca naught times X concentration of B. All of you know that moles Fa at any time, if you write Fa naught initially is Ca naught initial concentration times the volumetric feed rate, which we have already discussed in the design. So, if you look at this rate equation, this is your design equation, or one can write, as I said, in the form of Fa naught dx by dw is equal to minus R A dash. For the catalytic reaction, generally we use this, where dW is the mass of the catalyst, which will depend on the density of the catalyst in the bed, rho B times this volume dV, right. So, dV is AC times dz. So, one can write the expression in either form. V is constant volume system, volumetric feed rate, and superficial gas velocity is also important when we look at a design of a system when the catalyst deactivates. So, that is volumetric flow rate divided by the area of cross section of the reactor. The epsilon is the fractional change in volume, and since it is a constant volume system, so there is no change in the volume during the reaction. T is temperature under isothermal conditions. So, T 0, and P is the pressure P 0. So, this is what the expression in terms of rate law. So, one can write minus R A, which is a deactivation function times the density of the catalyst in the bed times whatever the K C A divided by 1 plus K C A, which is at any time, and assuming that the second term K C A, which C B, C A minus C B. So, here we have assumed that the reaction is irreversible. So, one can very easily write this expression, and as I discussed that this is your dxa by dz, which is written in this expression here. So, we have substituted this in form of dxa by dz. So, your expression which comes out in this form dxa by dz, because Fa naught dxa by dz is equal to minus R A into A C. So, one can write this R A in terms of dxa by dz, and I told that this deactivation function most of the time these are empirical correlation. So, here the deactivation function is defined by phi is equal to 1 divided by 1 plus A t to the power half. So, where this is a kind of empirical expression, right, where this A is a constant and n, which I defined earlier, is half here. And time which we are talking again here in a reactor, this depends on the superficial velocity. So, V naught suppose is the volumetric feed rate, and AC is the area of cross section of this tube. So, I defined that V naught volumetric flow rate is related to some molar flow rate, right. So, that V naught into Ca naught concentration is your total molar flow rate of A, that is one term. Second term, is the superficial gas velocity. So, superficial gas velocity u is defined by volumetric feed rate divided by the area of the cross section, right. And this u is superficial gas velocity. If I say that z is the height of the reactor, then this time to travel from this point to this point is this time when the catalyst gets deactivated. So, what is the activity of catalyst after this time t, that can be correlated in terms of height of the reactor and the superficial gas velocity. So, one can correlate this t by z divided by u, superficial velocity, and this term t which is written here is given in terms of z, that is divided by u to the power half. So, since u is superficial gas velocity and in this case it is assumed constant. So, that has been taken here in a dash. So, this is what t is equal to z divided by u, where z is the height of the reactor and u is the superficial gas velocity. So, this term which is a t to the power half and t is given by z upon u to the power half, this term will come like this, and a divided by u to the power half has been written here a dash times z to the power half. So, if you look at or you combine your expression now here by substituting C A naught 1 minus x a, right. So, that expression has come now in this form, d x a by d z is equal to, all other terms are mentioned as usual here, times 1 minus x divided by 1 plus k a C A naught 1 minus x times the phi, which is the deactivation function. So, one can very easily write either in terms of the bulk density or in terms of the volume of the reactor and volumetric feed rate. So, this is the how the deactivation function and the main rate of reaction are correlated. So, now one can design the reactor or one can find the conversion x for a given height, or if the conversion to be achieved is fixed, then one can find out the height of the reactor when the catalyst is deactivating. So, this is a kind of that sizing a reactor or design a reactor for the given system when the catalyst deactivation is significant because of carbon formation. So, accordingly we have either the fluid catalytic cracking, as I said, that a fluidized bed reactor system, or we can have a straight through transport reactor, or which is a kind of moving bed reactor. So, catalysts are continuously taken from bottom to the top and their activity is measured, and then they are sent to a second column which is the regenerator, right, and then recycled back into the system. So, that is known as straight through transport reactor, or it is a kind of a simple moving bed reactor. So, this is just an example for practice. So, here if you look at the problem is something like that, a gas phase cracking of light gas oil is carried out in a straight through transport reactor. So, that what I was talking, the straight through transport reactor is basically a tube like this, where you pass the feed from the bottom. So, feed is taken like this and it can be co-current, it can be counter current. So, feed along with the catalyst. So, catalyst particles are taken like this. So, here catalyst particles are slightly larger compared to a fluidized bed reactor. So, in the case of fluidized bed reactor, the bed is to be fluidized. So, particles are smaller in size, right, say 1 micron to 50 micron, 100 micron, depends on the type of particles and the velocity. So, one needs to identify. Here the particles can be larger, say it can be 100 micron, it can be 0.5 mm. So, one can take the accordingly, and particles are moving in the bed like this, and then you have a kind of reactor system here or a hopper system for the separation of the catalyst. So, disengaging hopper here. So, catalyst separates and the feed product goes here, unreacted feed and products are taken in a separate unit and condensed, and the catalyst comes down here and falls like this and comes into a reactor, another reactor which is a regenerator basically, where oxygen is passed from the bottom or air is passed from the bottom, right. The flue gas will go out like this and the catalyst is burned here and then regenerated and taken back into the system here by some lift gas. So, you need a lift gas here. So, this is a kind of some rough geometry of a moving bed reactor, or also known as straight through transport reactor. So, different designers or different licensors have given different kind, Kellogg has one, UOP has another one, right. So, different kind of designs are available for the hydrocarbon cracking. So, it can be atmospheric gas oil, vacuum gas oil, naphtha, all these. So, here this is what the height of the reactor to be decided in terms of the activity of a catalyst. So, when the catalyst comes here, its activity drops. So, we are defining some kind of average activity and average conversion down the length of the tube or throughout the tube, depending upon the superficial gas velocity. So, if you look at here, the product, the gas oil is to be carried out in a straight through transport reactor and temperature is given 750 degree Fahrenheit with catalyst that decays by coking. So, deactivation of a catalyst is there because of the carbon deposition. The concentration of the feed is given Ca naught 0.2 kilomole per meter cube and the catalyst particles are assumed to move with a mean gas velocity which is given here UG and that is constant here is equal to US and that is equal to 7.5 meter per second. Rate law is given. So, kinetic rate constant K times rho b is given 8 second inverse. So, first order rate constant, Ka is the equilibrium constant. So, 3 meter cube per kilomole and Kb is for the product equilibrium constant. So, 0.01 meter cube. Rate of reaction minus Ra per unit volume of reactor is Ra dash times rho b and that is related to some deactivation function times your Langmuir-Hinshelwood type mechanism. So, rho b times Kca divided by 1 plus Kca plus Kcb. So, this is a gas oil and converts to product. So, product may be gasoline, gases, everything, right, and plus the coke. So, phi is the deactivation function which we have defined earlier also and given here by 1 divided by 1 plus A t to the power half with A value is given 7.6 second inverse minus, that is second to the power minus half, right. Neglecting the volume change during the reaction. So, epsilon is given 0 here and there is no pressure drop in the reactor. Determine the conversion as a function of distance down the reactor. So, one needs to find out the conversion as a function of z. So, the expression dxa by dz which I was talking earlier, that is to be defined and here the value of z is given 6 meter. So, for a 6 meter long reactor, the expression which we have defined like this, the same is to be used here in terms of the deactivation function. So, that has been just discussed here. So, as a practice you need to check that and calculate. So, mole balance equation, that is Fa naught dxa by dz is equal to minus Ra into Ac. So, one can write it in terms of mass of the catalyst or in terms of the volume of the reactor. So, Fa naught dxa by dz is equal to minus Ra into Ac, this is your mole balance equation. Rate law has been defined. So, that is minus Ra is equal to 5 times rho b times Kca divided by 1 plus Kca. And one needs to identify this, right. It can be 1 plus Kca plus Kbcb also, right. So, that here we are assuming that this mechanism is already known and rate law is known to us. And here the stoichiometry A gives you B plus C. So, B is your product and C is your carbon and Ca is defined by Ca naught 1 minus Xa. So, that part we have already discussed earlier also. So, Ca is equal to Ca naught 1 minus Xa because epsilon is 0. If there is epsilon value, then all of you know that Ca is defined by Ca naught 1 minus x divided by 1 plus epsilon x, where epsilon is the fractional change in volume and defined by Y A naught into delta. So, Y A naught is the mole fraction of the limiting component and delta is the change in stoichiometric coefficient of the product and reactant. So, this is something like, suppose small a gives you a B moles of B, then for this delta is simply B minus A, right, or one can write it in terms of A is equal to B upon A times B. So, epsilon will be, that is Y A naught is 1 in that case, that depends on the mole fraction, right. If inerts are added, it will change, but suppose if I say pure A is there, then y a naught is 1, and one can write with delta, which is difference in the stoichiometry of this product minus reactant. So, one can define. So, in this case epsilon is 0. Same thing for C B, because 1 mole of A gives you, here the stoichiometry is given like this, right, plus coke is a solid material. So, 1 mole of A gives you 1 mole of B. So, whatever the moles of A reacted, equal number of moles of B will form, right. So, F A naught is the inlet mole. So, F A naught 1 minus x is the moles of A which is left if you make the stoichiometry table, and F A naught x is moles of A reacted. So, F A naught x of moles of B will form, right. So, that is just the concentration of B in terms of the product which is written here, C B is equal to C A naught x. The volumetric flow rate, as I said, V is equal to V naught, and U is superficial velocity, V naught divided by the area of cross section of the reactor. So, one can very easily combine, as I discussed. So, I am not going in detail of this. So, dxa by dz is equal to this equation, which is simplification of this times 1 minus x divided by 1 plus k C A, which is C A naught 1 minus x times the deactivation function. So, this equation can be solved numerically to find out x as a function of z, right. So, one can use the MATLAB or Polymath, or the any kind of ODE can be used to solve this kind of equations, right, which are now the tools are available, or one if possible one can solve it analytically also. And one can plot the equations like this in this form. So, this is the activity profile, which says that activity of the catalyst decrease with time on stream or as a function of z. So, here this time on stream is up to the length of the reactor, which is given here as such up to 6 meter here, but one can have the profile to a different length also, and one can decide that to what activity the reactor can be operated, that is mode of operation of the reactor till the catalyst deactivates or till activity reach to a level of the say 50% or 20%, 30%, it depends on the type of the reaction. So, here one can see for 6 meter the activity drops to a level of this, which is roughly here say 0.35, right. So, one can very easily look at that, and conversion, this is increasing down the length of the reactor. So, as you go up, the conversion increase like this. So, one can plot the conversion or the activity as a function of time or the length of the reactor. So, this is what the deactivation because of the coke formation, what I discussed, and because it blocks the active site, and because of the blocking the active site or pore of a catalyst, the rate of reaction decrease. So, one needs to reactivate or regenerate the catalyst by burning with oxygen and remove the carbon deposited on the catalyst to certain extent, so that the activity can be maintained. The another kind of catalyst deactivation which I was talking is because of sintering, right. So, sintering is the loss of activity of a catalyst, right, caused by prolonged exposure to elevated gas phase reaction temperatures. So, as I said that when the catalyst is continuously exposed to a high temperature value, then the activity of the catalyst decrease because of the change in phase of the catalyst, right. So, it is something where the agglomeration takes place, which I discussed earlier, and this because of this agglomeration the particles gets sintered, right, and this is nothing but the growth of the crystal size. So, smaller crystals they agglomerated and made a larger crystal. So, this is because of the sintering, right, and this sometimes reduces the pore size of the catalyst, and also there is a phase change, right, phase change due to temperature, right, temperature reaction I will say, because high temperature reaction, right, solid material they react together, or nickel reacts with alumina say and form nickel aluminate. So, this is a kind of phase change, and therefore, the activity of the catalyst decrease during the course of reaction. So, mechanistically if you see here the crystal agglomeration, right, or growth of the crystal, reducing the internal surface area accompanied by narrowing or blocking the pore of a cross section. So, that is again a very common phenomena, especially when the catalyst is treated at high temperature, right. High temperature, say zeolite catalyst cannot sustain temperature more than 550 or 600 degrees centigrade. So, if the reaction is required at higher temperature, then one needs to stabilize the catalyst, so that this should not agglomerate, or the active sites of the catalyst should not grow if you need especially a smaller particle size during the reaction. So, that becomes very important when you look at the deactivation phenomena, and especially where the phase change. So, because of the high temperature and time, there is a kind of solid reaction between the metal and the support, and they get transformed into a different phase, and that decrease the activity of catalyst. So, one simple example, say in the case of Fischer-Tropsch reaction, the iron or nickel, they form some kind of nickel carbonyl iron carbide, but sometimes the particular phase nickel carbonyl, say it may not be desired for the reaction, or iron carbonyl may not be desired. So, that drops the activity of a catalyst. So, loss in active surface area, which results from prolonged exposure to high gas phase temperature, right, that is undesired, and occurs in both supported and unsupported metal catalyst. So, when you have a nanoparticle, so they will get agglomerated and activity will drop. So, that is what I said, that nanoparticle preparation may not be too difficult, but to make them stable during the catalytic reaction, especially when the temperature is high, that is a difficult or tedious job. So, two models are generally here used in terms of the crystal growth because of the sintering. One is known as atomic migration, where atoms migrate, and second is the crystal migration, where the total crystallite which form during the reaction, they migrate, and it may be through surface diffusion. So, which is something like here. The particles, if you look at here, these two particles, they migrate on the surface because of the temperature time, right, and they get agglomerated, form a larger. So, this is what they coalesce here, right. So, the crystal grows in size, right, and same thing is the here the surface or through the gas phase. So, they migrate and get agglomerated, and this is the example of sintering. So, the reduction can be defined, or activity of a catalyst can be correlated by decrease in surface area of the catalyst per unit mass of a catalyst, right. And same thing here, they get migrate here, and then they come here, and so this is kind of migrating molecule, they come in the stable form like this, metastable. So, they migrate and they get again agglomerated, and they move to the pore and they block the pore, right. So, all kind of mechanism may be possible during this sintering. And the consequence of sintering, just for an example, if you take alumina support and no metal part, even there is no metal part, the surface area of the alumina, if you look at it around 850 degrees centigrade Kelvin. So, it is roughly 190 meter square per gram, but when you give the temperature treatment or you heat it to a different temperature range, then the surface area change, because the phase transformation, right, or the agglomeration. So, it is a porous material, and here it becomes a kind of non porous material, a kind of alpha alumina which you get here, and this may be a kind of gamma alumina here. So, that is what I told, that there is a kind of change of phase, or there is a kind of change of the structure of the crystallites, right. So, there is a decrease in the surface area of the catalyst. So, when the surface area is less, your active sites will reduce accordingly, or preparation, when you do the catalyst preparation, it becomes difficult, and finally, the agglomeration of the pore because of the low pore volume or low surface area, and overall rate of reaction will decrease because of this phenomena. So, it is a kind of aging, right, because temperature time relation for how much time and how much at how much temperature the catalyst has been in contact, right, in that environment of high temperature and time. So, the activity loss, right, or loss of active sites which I have discussed, right, and because of the agglomeration. So, that kind of mechanism, although the details are not available, and lot of R&D may be done to understand for a given catalyst, for a given support material, and how do they agglomerate, that is how the crystal size grow, or when you have a nanoparticles, how do they grow during the temperature time treatment, and one can identify the mechanism and find a solution for that in order to reduce. So, catalyst, the promoters can be added to reduce the active site, just like as an example, if you have the iron catalyst, right, or a kind of say cobalt catalyst. So, if you add some kind of copper promoter, so copper comes in between the two iron particles and it prevents the agglomeration to some extent, either copper or that is either cobalt or iron, which are generally used for the Fischer-Tropsch reaction. So, there are different kind of promoters can be added to enhance or improve the stability of the catalyst, which is because of the sintering phenomena. So, in the case of commercial reactors, if you look at the activity of catalyst which decrease with time on stream. So, generally the options are either you regenerate the catalyst, or second option can be that increase the temperature, because the rate of reaction will increase or your rate constant will increase when temperature is increased, and in order to compensate the decrease in activity of a catalyst, that can be compensated by increasing the temperature. So, that part I will take little later, but if you look at the deactivation mechanism because of sintering. So, just like in the case of poisoning or fouling, we have discussed that the activity drops as a function of some deactivation function. So, minus dA by dt all the time, but we write here is something times k d times the activity to the power n, something like that, right, where A is a kind of activity function, or this whole thing can be written in terms of the, when I write rate minus R A can be written in terms of R A 0 times some function of this, which can be calculated from this. So, this is basically activity of a catalyst, and how does it drop will depend on the mechanism of the catalytic reaction. So, this drop in activity, as I said, may be because of fouling, may be because of poisoning, or may be because of sintering. So, this similar expressions, that is the deactivation order which I was discussing here n, right, and the rate of deactivation, that is the kinetics of deactivation, if you look at, that can again be discussed just like the kinetics of the main chemical reaction, that is a first order deactivation, second order deactivation, or any nth order deactivation. And these can be find out just by the same method like first differential method of analysis or integral method of analysis, right. So, same reactor, that is the catalytic reactors which are generally used for screening small in the differential form, they can be used to determine the deactivation function during a catalytic reaction, or when we screen out the catalyst, then activity of a catalyst can be measured for different catalysts. So, this n is a kind of order of deactivation, and this can be find out by assuming say first order deactivation or second order deactivation. So, in the case of sintering, generally it is assumed as a second order deactivation. So, that can be correlated like this. So, minus R d, which is the rate of deactivation, is equal to minus dA, R d is the rate of deactivation, is related to minus dA by dt, that is decrease in activity with time, and that is related to k d times A square, which is for the second order deactivation. So, this is a second order deactivation, and now one can integrate, because by separating the variables. So, minus dA divided by A square is equal to k d t, which is written here, right. So, dA divided by A square is equal to k d times 0 to t dt, and how the limit will change, because when the catalyst is fresh, the activity is 1, because activity you define rate at any time divide by rate when the catalyst was fresh. So, at t is equal to 0, the catalyst is fresh. So, rate R A and R A 0 are same. So, your activity for a fresh catalyst will be 1. So, for t is equal to 0, activity is 1, and at any time t the activity drops to a value A. So, one can integrate this expression, right, and the simple dA upon A square, right, and here it is minus 0 to t. So, this is simply time. So, one can write the expression if you integrate this by substituting the limit. So, A t is equal to 1 over 1 plus k d t. So, this is a kind of expression for deactivation because of sintering, or especially where I am saying in general a second order deactivation. So, this just says that the activity of the catalyst will drop with time on stream, and in other words I can correlate it with surface area of a catalyst, right. So, because sintering means growth of the particle. So, because of that surface area of the catalyst decrease. So, in that case how surface area decrease because of the time on stream is because, and that is correlated with the activity of a catalyst. So, one can correlate S A, which is surface area at any time T, just like the rate at any time, is nothing but initial surface area multiplied by the activity of a catalyst, and that we have already defined here. So, this is simply S A 0, which is the surface area of the fresh catalyst, and times this deactivation function, which is 1 divided by 1 plus k d t for second order deactivation. So, one can write the expression for different type of deactivation functions. So, centering equation, if you look at with time on stream, again this whatever the k d which we are writing, that is related to temperature, right. So, one can write k d is equal to k d at T 0, which is at some reference temperature, times exponents of E d, which is the activation energy for the deactivation reaction, divided by the gas constant times 1 by T 0 minus 1 by T. So, this is the k d calculated at any temperature T, right. So, why do we need this? Because as I said that sometimes in order to compensate the decrease in activity can be done by increasing the temperature. So, although when you increase the temperature, the deactivation rate constant will also increase and rate constant for the main reaction will also increase, right. So, depending upon the activation energy of the deactivation reaction and main reaction, which we will talk little later, and one can see how much temperature should be increased or how much temperature is to be increased in order to compensate the decrease in activity of the catalyst. So, that is very important, especially when the activity drops faster and regeneration is not possible. Say in the case of kind of fixed bed reactor, the regeneration of catalyst may be difficult. So, in order to maintain the activity, the temperature, say after 6 months of operation, the temperature can be increased by 10 degrees centigrade or 50 degrees centigrade to a maximum whatever the permissible limit, in order to get the higher productivity. And this is what I was talking, how to look at that, how to find out that how much temperature is to be increased, you need to find out a temperature time trajectory, right. So, this is important, is not when the catalyst deactivation is fast, very fast, just like as I said the catalyst deactivates continuously, and when you have a fluid catalytic cracking or moving bed reactor, this kind of temperature time trajectory may not be effective, right. So, this is effective only when the deactivation is slow, right, or activity drops at a slower rate. So, in order to maintain the activity, one can increase the temperature after certain time, or one can have the temperature time trajectory something like this, right, T versus time. So, what is the meaning of temperature time trajectory? It is simply that it is a control strategy which involves maintaining a constant conversion with catalyst decay by increasing the operating temperature, right. So, develop a temperature time trajectory, and which simply says that if you know the rate at any time t, right, which is lower, because rate at any time t will be related to the rate at t is equal to 0 multiplied by the activity of a catalyst, which we have already discussed, and this activity of a catalyst decrease with time on stream. So, if somehow we know that how this activity decrease with time, that is if deactivation function is known, then one can increase the temperature accordingly, because when you increase the temperature, then rate constant will increase from Arrhenius law, right, Arrhenius equation. So, it means this R A at any time t will be now R A at some higher temperature t, right. So, what we have done, that whatever the drop in this activity with time has been compensated by increasing this value, right, by increasing the temperature at that time. So, how much temperature is to be increased, that can be correlated by using the Arrhenius equation. So, that as I said, the temperature will affect the deactivation rate constant as well as the rate constant for the main reaction also, but one can correlate these two. So, look at here that K at any temperature T, which is the rate constant for the main reaction, will be related to the activity, because this expression. So, R A, which is written here R A dash at t and time, is nothing but activity multiplied by that time and temperature times the rate constant for the main reaction, and that is equated to the rate when the catalyst was fresh, right. So, concentration is same, the relation is made now with respect to the Arrhenius expression, which is now rate constant evaluated at T 0, right, temperature T 0. So, this is a kind of reparameterization. So, this is not the pre-exponential factor, this is the rate constant measured at some reference temperature T 0, right. So, one can write this because k you know from Arrhenius equation k 0 e to the power minus e upon R t, that is the Arrhenius equation. But when I am writing k 1 by k 2, so that is represent this is the now rate constant measured at temperature T 0, right. So, this is the rate constant which is measured here at temperature T 0. So, this is rate constant measured at temperature T 0 times e to the power e upon R 1 by T 0 minus 1 by T, and that is equated to the initial rate, that is when the temperature is T 0. So, what is done here, if you try to correlate. So, rate constant generally you define k is equal to some pre-exponential factor which is k 0 dash e to the power minus E divided by R t, where E is the activation energy for the reaction and T is the temperature in Kelvin. So, if I write rate constant at two temperature K 1, this is T 1 and another temperature K 2, this is again K 0 dash E x p minus E divided by R T 2, right. So, this now here in this case what we have done, T 0 has been taken as a reference temperature and T at any temperature we have eliminated these two. So, K 1 divided by K 2 is equal to this cancels when you take the ratio. So, E x p minus E upon R 1 by T 2 minus 1 by T 1, or one can write it in this form. So, this is the what expression calculated in the form of K 1 by K 2. So, which is just now E x p, right, and that will be defined in terms of E upon R 1 by T 1 minus 1 by T 2, something like that. So, T 1 is your T 0 here and T 2 is any temperature T. So, this K 2 will become your K 0 here in this case, right. So, we have written this as a reference temperature. So, this will be basically in the form of this K 1 is your now any temperature T and K 2 I have taken here as a reference temperature, or one can write in terms of the ratio of K 2 by K 1, that time you will get the expression similar to that. So, basically E x p minus E upon R you take out. So, this is simply 1 by T 2 minus 1 by T 1, right. So, that is what one can simplify. So, this is the expression which is written here, and now if you use this expression you can very easily find out, because K 0 cancels. So, one can write the expression for activity, right. So, from this equation this 1 is equal to e to the power E upon R E A upon R, where E A is the activation energy for the main reaction 1 by T 0 minus 1 by T. So, one can write from this, if you take log. So, this times log of A is equal to whatever the expression here written in the form of 1 by T. So, one can write it 1 by T minus 1 by T 0 is equal to simply R upon E A ln A, right. This is from this equation 1 upon T or 1 upon T minus 1 by T 0. So, I have taken it other side. So, R upon E times ln of A. So, that is the expression how temperature and activity are correlated if this is known at temperature T 0. So, activation energy for the main reaction is known from the kinetics, right, and one can find out what is the activity as a function of temperature, and once this activity is known, this can be substituted in the deactivation equation. So, this is your decay law. So, your rate of deactivation or the rate for the deactivation is related to the activity. So, R d is minus d A by d t, that is equal to K d times, again it is related with the Arrhenius constant, right. So, K d is at some reference temperature, that is measured at temperature T 0 times e to the power minus e to the power E d upon R now times 1 by T 0 minus 1 by T, right, and times A to the power n. So, basically we have written our deactivation equation minus d A by d t is equal to K d times A to the power n, and K d can be correlated just from Arrhenius equation. K d 0 first I will write here, which is pre exponential factor, times E x p minus E d divided by R T, that is the expression which is written here, right. And again as usual as done in the earlier case. So, we are calculating the ratio K D 1 and K D 2. So, K D 2 divided by K D 1, just like because the at temperature T 1 there is some constant, deactivation constant, and at T 0 there is some deactivation constant, and this because Arrhenius equation will tell how the rate constant increase with temperature. So, rate constant for main reaction is also increasing, and for deactivation it will also increase, right. So, for both main as well as the deactivation reaction the rate will increase. So, this is something like A gives you R and A gives you kind of Poisson precursor, right. Here we are correlating it with the sintering. So, this is also increasing rate constant, and this is for deactivation reaction, and this is also increasing, right. So, one can correlate. So, one thing is from, so what is the activation energy for this reaction, what is activation energy for this reaction, and you can see the relationship between the rates, or if I just look at the desired product divided by undesired product, one can find out from that also. So, this R D which we have defined. So, now we can substitute the value of activity here from original equation which is from the main rate. So, dA by dt is equal to K D 0 which is written now in terms of that temperature time relationship which we have defined, temperature activity relationship. So, K D 0 e to the power E d upon E A ln of A times A to the power n, and that becomes, if you simplify this equation, this becomes K d 0, right, A to E, which is here combined term. So, this E to the power E d upon A. So, I can write it ln of E d upon E A to the power A to the power E d upon E A, negative sign, and this now has the same unit. So, one can just take it together. So, n minus E d. So, this is n here, and this is minus E d upon E A, right. So, this can be written in terms of power here. So, this expression which this K d has been replaced from here, which is your original equation here. So, we substituted the value of activity, right. So, or in one way you can say substitute the value of 1 upon T minus 1 upon T 0, that is equal to R upon E A ln of A, right. So, from this equation the value is substituted here. So, 1 upon T 0 minus 1 by T, and that has been changed to R upon E. So, which is cancels now, because this R and that R gets cancelled. So, finally, you have minus E d upon E A and E A upon E d upon E A ln of A. So, that can be written in terms of the power form. So, K d 0 A to the power n minus E d upon E A we get, right. So, once this is known, now the integration can be done for the expression. So, because you have already obtained this relationship for temperature versus activity, that is 1, right. The expression for activity is now related A e to the power E upon R 1 by T minus 1 by T 0, right. So, minus R A which is R d is equal to minus d A by d t is equal to K d to the power n. So, one can integrate, because now activity is known in this form, right, from your original equation. So, integrate this equation for the limit again as usual, that t is equal to 0, activity is 1 and to any time A, right, at any time t activity is A. So, one can integrate this expression and find out the time for achieving a given activity. So, that is it is something like that. After time 6 months, say what is the activity of a catalyst, right, which is correlated with temperature now, that is how much temp, because it will depend on E d upon E A value, that is activation energy for the deactivation reaction and activation energy for the main reaction and order of reaction. Suppose n is 1. So, this is just A to the power E d upon E A. So, one can very easily find out whether activation energy for deactivation reaction is higher or main reaction is higher, right, and accordingly after how much time the activity will drop to some value 50% say 8.5. So, how much is the time? So, one can find out, because all other terms are known now, once the mechanism of the main reaction and mechanism of the deactivation reaction is known, right. So, one can very easily substitute these expression in other forms and get the expression in terms of temperature and time, right. So, this is what the integration has been shown here, 1 to A to the power minus n times E d upon E A, which is this expression, right, d A, and that is equal to other side minus K d 0 0 to T d t, because this is your R d, right, is equal to minus dA by dt is equal to kd times a to the power n, and that is the expression which has been integrated to find out this time, right. So, one can calculate this, and the only limit here is that E d upon E a minus n should not be equal to 1, right, otherwise it will be indeterminate form. Same thing for the selectivity also, because the when there is a deactivation, the catalyst activity is decreasing, and because of that a selectivity may also be affected, right. So, there are different influence, diffusion resistance may also have influence. So, that we will see little later, that depends on the time permitting, right. So, this expression which is on selectivity effect, that if you look at just an example, we have considered a parallel reaction here. A gives you the desired product D and A gives you undesired product U, right. So, how do you define selectivity and yield? So, generally yield we define, suppose the reaction gives here, given here is D and U. So, D is the desired product, U is the undesired product. So, yield of D, so yield generally defined for the desired product. So, moles or mass of the desired product D produced, right, divided by moles of A reacted. So, this is the definition of yield, right. But the more important thing here is that selectivity. So, selectivity which is defined here in terms of desired product to the undesired product. So, S for D will be defined moles of D produced divided by moles of U produced or formed, right. So, what is our aim? We have to maximize this D formed per unit moles of U formed, and that is again a function of your temperature time relationship, because of deactivation, because rate of formation of this will be different, rate of formation of this will be different, and deactivation minus dA by dt, that is A1 for this will be different, and minus d A2 by dt for this will be different. The order of deactivations may be different, deactivation kinetics may be different. So, it means it will depend on the overall mechanism of the main reaction as well as the mechanism of the deactivation reaction, and objective will be how to maximize this selectivity, right. So, here just as an example, if you look at the selectivity with respect to U du, which is defined R d divided by R u, that is the moles or mass of the D produced, rate of production of D divided by rate of production of U. So, that is defined by d C d by dt divided by d C u by dt, which is rate, right. And this rate is formation is in terms of related to the some function of the main reaction. So, rate constant for D, this is not deactivation, the rate constant for D times K C A to the power n. So, we are writing minus R A is equal to K C A to the power n. So, this is the main reaction kinetics multiplied by the deactivation function for the main reaction, right, and divide by same thing for here. So, main reaction kinetics for U formation times its deactivation function, right, and that simply becomes now K D divided by K U C A to the power n minus m. So, it will depend on the order with respect to main and the Poisson reaction times the phi 1 by phi 2. So, this is again it may not be same phi 1 and phi 2, right. So, that is what the overall selectivity for D formation. So, now d phi 1 over dt, which is your deactivation rate for first reaction, that is D formation. So, K d d deactivation constant times it can be some activity power, right, phi 1 to the power p, and it may also depend on the concentration of the feed or may not, right. So, if it depends on the concentration of feed, it is more generalized. So, C A to the power some r, right. Same thing for decrease in activity for second reaction, which is minus d A by d 2 or d phi 2 by dt, either way one can write, is equal to R d u time, and that is equal to K d u, that is deactivation constant for U formation times its A, that is activity of that second reaction towards second reaction to the power q, and times the concentration of A to the power s. Again here we have assumed that it may depend on the concentration of the Poisson precursor present in the feed, which is related to the concentration of the main feed. So, one can integrate the expressions and find out what is how phi 1 change or activity for first reaction change and activity. So, this is 1 to phi 1 as usual, d phi 1 divided by phi 1 to the power p. So, separation of variables, right. So, integration by separation, and one can find out the phi 1, which is something like this. So, you can do it for your practice, right. So, just integrate this equation, and phi 1 is equal to 1 minus p plus 1 times k d d C a to the power r times t to the power 1 over 1 plus p minus. So, here it is just time, and this is you know that it will be just minus p. So, p plus 1 minus p plus 1 divided by minus p plus 1, and that is what get written here. Same thing for the second reaction. So, one can relate phi 2 also, and these can be substituted in the main reaction, which is written here, right. So, S du is equal to R d upon R u, which is written in terms of these two rates, and can be correlated with the k d times C a to the power n, which I already talked, and that can be now substituted because this ratio is known now. So, this is just the substitution of this term here, right. So, how the selectivity change because of deactivation will depend on the orders, right, of each, that is the first one towards D and the second one towards Q, right, or U, and also the concentration of the feed, if that depends, right, and that will change with time on stream. So, one can write the selectivity expression for the product, and overall it will depend on n minus m also, if that change, that is the order is different for main reaction, that is formation of the D and formation of the U. So, one can very easily find out that how selectivity change with the reaction, right, and can correlate with the activity of the catalyst. So, it means that the activity of a catalyst change, or because of that the selectivity towards a particular product or desired product may also be affected. So, deactivation may have many consequences, right. So, one needs to understand the mechanism for catalyst deactivation for a given reaction and selecting a given catalyst, because it may change from catalyst to catalyst also. So, all kind of deactivation need to be studied, and then it should be incorporated in the main reaction, and finally, for the reactor design, because the selection of catalyst or screening of catalyst will depend on the stability of the catalyst also, which is a part of the catalyst deactivation. So, I stop here and thank you.